Hi, I've got one last Monte Carlo technique I want to talk to you about. This will be a short video. It's just going to be a single slide, but we'll talk through a couple details of it. So one more approach that's useful in these Monte Carlo simulations is called metamodels. And the idea here is we can draw a little sketch. And let's just do it in one dimension to keep our picture simple. So if I've got kind of x, and I have, well, we could actually just do g of x. So my function is telling me whether I've got a safe outcome or a failed outcome. If that thing's really expensive to evaluate, then Monte Carlo simulation is tough because I'm generating these thousands or hundreds of thousands or millions of samples and evaluating that function many times. And so as a way to try to avoid that, I can do a few samples, maybe not too many, and I'll carefully choose them. So let's say these are samples, are kind of evaluations. I've got a few samples of x, and then I'm going to evaluate the real function. And then rather than continue on with thousands or millions of these samples, I'm going to fit some sort of a simplified function to it. Or I'll try to find a function that passes through the data I sampled. And that's my meta model. So it's going to take the place of the expensive function. And so let's note that the real function is expensive to evaluate, it's slow. But that fitted function could be a polynomial function or something like that. And that's going to be very fast to evaluate. Okay? So the idea is if we fit this function, we can probably most importantly reduce the number of computationally intensive simulations. Now I can, this red function, if it's really easy to evaluate, I could call it thousands or millions of times, and that's not a big problem. But if the blue dots was a structural analysis or some other computational numerical model, I don't want to be doing that thousands or millions of times. I'll save myself the effort by fitting this meta model and then using the meta model in place for my reliability analysis. It also potentially has this benefit of reducing the number of random variables. So if I fit my model and I see that some of the random variables don't play a significant role in my outcomes, then I could just drop them out of the model as well and simplify my problem. So I can learn a little bit about the problem and simplify it as well. Okay. So some examples, we do this response surface analysis. So that's fitting polynomial or something like that. You can do regression analysis is effectively a meta model. It can be used in that way where you fit a regression model and then use that. You can use these support vector machines as a machine learning version of linear regression. You can use Gaussian process regression is another one that's popular. So there's different flavors of basically what's the functional form of the meta model. So Gaussian process regression, this is also, depending on what field you're in, this also gets called Kriging, just a couple names for the same thing. So when you do this, you've got a couple decisions to make. One is how to represent the meta model. Which of these is an appropriate model for what I've got in terms of representing the relationship between the input random variables and the outcome I'm interested in. And the second decision is where to take the initial samples. That's right. So that's the blue points up in that top right figure. So when I've got just one dimension, that's pretty easy to draw. I just say, let's just take some samples spaced out over the range of x that I'm interested in. But if I've got two x's, now I have to choose in a planar space. And when I've got high dimensions, I'm going to end up taking a lot of samples if I'm trying to cover all the combinations of input x values. And this gets called experimental design. And so the idea is that the initial blue points in that top right figure, those are my experiments. Well, I'll go collect some data. And once I've collected that data, I can fit this meta model and I'll just use that moving forward. Okay. So that's a quick look at meta models. And that's an approach that is used in structural reliability reasonably often. And hopefully at least the basic concepts you've got some familiarity with. Okay. So that's our last technique. With the next video, we'll start wrapping up and making some concluding comments.